outlines, and then we'll solve exercises given as assignment. Okay, so let's begin with recalling what was done in the this week. So first session is about problem solving. There are 4 5 uh, beautiful problems that have been solved by the professor. So from the second video onwards, we what we learned that I'm going to recall. So first part is about isometries. What are isometries? Isometries are basically functions uh, from C to C, such that if 2 points are, let's say, delta distance away, their images are also delta distance, exactly delta. So we can write f from C to C such that uh, f of z minus f of w modulus of this is same as modulus of z minus w for every z. So these kind of functions are called isometries, and some facts about isometries that we have seen in the classroom is that isometries, they preserve the inner product which was defined in the previous week. So isometries preserve uh, the inner product defined previously. The inner, which was defined like inner product of Z and W. This was the real part of Z, W part Z. And the second fact which was uh, proved was this, that when f of 0 is equal to 0, then f is linear, f is R linear. And the third fact about linear isometry, so in this case it is called, f is called linear isometry. And the third fact was about linear isometry. They are either rotation or they are reflection. And linear isometry are either rotation, rotation around origin, or reflection around a line passing through along reflection, right? So no need to write all that. So, and after this we learn what are polar representation of complex numbers. So uh, so here in this section, what we have seen is that for every z belonging to S1, where S1 is defined as, okay, so I should write another line, but S1 is defined basically those complex numbers which modulus is equal to 1. So this is called circle. So unit circle. So for every z belonging to S1, we have z is equal to e power I theta, or same as cos theta plus I sin, where theta is in this interval minus pi to pi. So from here, for every z belonging to complex number, we can write uh, kind of decomposition. So here, from here, what we conclude is for every z belonging to C, we can write z is equal to mod z into z mod z divided by mod z. Now, say this belongs to S1. So z can be written as R into something in S1, and from here S elements of S1 can be written as e power I. So this decomposition here, R is positive, it could be 0 also. When it depends on z. If z is 0, then only it. So R is positive number, and theta belongs to minus pi to pi. Here R, which is defined as modulo subject, this is known as length object or mod, modulo subject. It is called usually length object, or yeah. And magnitude, this is called magnitude or length, or I don't know, I don't remember right now, but theta is called, we'll fill this gap. Do you remember what this mod z is called? Hello, am I audible? Hello.
Absolute value and argument, right? Like,
No, no, theta is called argument. What mod z is called? Is theta is called argument of it. And mod z is called maybe length of z or something. So if you don't know, we'll see. It's just the name. Just remember by the length of z or what length of z. So after identification of complex number with plane R2, so every complex number can be understood as a vector inside R2. So in that notation, we call length of the vector. So same thing I'm repeating here. That mod z is called length of the z, and theta is called argument of the z, and it is not well defined. Theta is not well defined. It is discussed in the class, right? Because e power I theta and e power I theta plus 2 pi I. If you add or subtract 2 pi I many times, they give the same value, right? So that is why that theta is not well defined until and unless you fix the theta. If your theta is ranging, let's say minus pi to pi only, then it is well defined and it is called argument of, okay? Theta belongs here, minus pi to pi. Okay, so after these definitions, we saw what are rational functions, polynomial polynomial functions, and then power series and their absolute convergence. Okay, let me write. So first of all, rational functions are basically of this form, p by q, where p and q are uh, polynomial functions, or they are, in fact, we can take them NLT, but we have to restrict our domain so that they become functions. They should be well defined, right? So from C, what we remove, so where p by q where P and Q are some holomorphic functions or polynomials. We can take P and Q are polynomials, and this polynomial, right? And their domain, of course, we have to restrict whatever function we are taking. Polynomials, their function P by Q is function on the on omega, which is defined as complex plane minus zeros of Q. Wherever Q is becoming zero, we have to remove that part. Okay, so these are basically, and P and Q are co-prime. We can take if there are common factors, we can cancel them out. So P and Q we can take co-prime, and then we can say P by Q. These functions are rational functions, right? But their domain should be restricted. That we have to always. Then we saw the definition of uniform convergence, right? Uniform convergence. And what is uniform convergence? It's just sequence of functions from C to C, Fn and F. These two are, let's say, complex. They are functions. We say Fn converges to F uniformly if what happens. So a sequence, okay, Fn z minus F of z. This is sequence of complex number converging to F of z. Epsilon positive is, if given any epsilon positive, there exists n naught inside natural number such that Fnz and Fz they become less than, they become very close. I mean epsilon close. And note that this would be holding for every z inside. So if it is a single sequence of complex numbers, it converges. Then n naught depends on epsilon, but we are taking for all z. That makes it uniform. So this is important in the definition of uniformly convergent sequences. Okay, so same epsilon and same n naught work for all z. Okay.
One question I have here. So, how is it different from the like convergence of functions in on real numbers, real functions? So, that I could not understand. And here, epsilon should also be a complex number, right?
No, no.
And epsilon is a
So
real number.
I'll explain to you. So inside complex numbers, we don't have any order relation. Okay, and wherever we want to say something is very close or how much close it is, so we use real numbers. Okay, so why we are writing fnz minus fz modulus? It was initially complex number. When once we take modulus, it becomes real number, and we can compare two real numbers, not two complex numbers. Okay, so epsilon is
Okay.
always real numbers, and
Okay,
this
so
is
because we don't have any of strict ordering in the set of complex numbers, we have to, there is no, perhaps no other way, or maybe there is some complicated way, like
there is no other way. We I think for field, complex number is a field, and it has no ordering. It has a
hmm,
nice proof,
hmm.
but right now I
Okay,
don't remember the proof.
okay, sure. Yeah, yeah.
Okay, so see here we could say point-wise converge. This sequence Fn converges to a point-wise if for every z, Fnz and Fz are very close. Okay, or Fnz converges to Fz, but same and not for every z it is working here. So in the case we say it is uniformly convergent if same and not works for all z, because if you change the z, epsilon is same, epsilon is fixed. If you change z, and not will change. Maybe after 100th step, fnz and fz are epsilon close, but for different z it may be different and not. So we say uniformly if it is common for all z. So this is different from point-wise conversion.
Okay, I will just repeat. Just please check my understanding. So the
Hmm.
thing is that uniform convergence means when I take the sequence, there's a sequence of functions,
Hmm.
and there exists a single n naught dependent on epsilon, for
Right,
which for throughout the domain of the definition of the function, for every z, this the absolute value difference is less than epsilon, means it is uniform convergence. And
right,
suppose for every for every epsilon and every z, there exists an n naught of epsilon z, then it means a pointwise convergence.
right. So
Okay.
if you get common and not, we say uniformly. If for it, if it depends on z, what point you take, we say it is point-wise conversion. Okay, you understood properly. Good. Right. So after this definition, we saw some absolute convergence of power series. So actually, we write power series. Power is uh, their formal power series looks like a naught plus a1 z plus a2 z square plus and so on. But see, this can be understood as a function of complex numbers to complex numbers. If you put some z, it produces some z, some other complicated numbers if it converges. So, so the formal power series becomes function only on the domains where it converges. Where it does not converge, it doesn't make sense. Just like rational functions, see what we did, it becomes functions on t minus z cube, where q is not zero. So we have to remove that part. So it becomes function. So power series becomes means complex valued function. This is just formal thing. It is not a function yet. But wherever we say it is converges uniformly, this series converges absolutely. Sorry, not uniform. Converges absolutely if the sequence of real number a n z to the power n, take modulus of this n from 0 to infinity, this converges. Now it is sequence of, sorry, series of real numbers, right? Converge. This is now series of positive real numbers. If it is converging, we say converges absolute. Right. So I want to ask one question: when a series converges or absolutely converges, what happens to nth term? Where this sequence goes? A n that should work. Or it happens to be that in this scenario it converges to zero. Okay, right. It's just like real number case. So not all power series gives us complex valued functions on complex numbers, but we look out exponential. We defined exponential oh, function, which was defined like e to the power z, which is same as this power series 1 plus z plus z square by 2 factorial 1 factorial. plus z cube by 3 factorial, and so on. We saw that this power series converges absolutely for every z. So for every z, it gives us a complex number. If you change the z, you get a complex number, which is called e power z. So this series converges absolutely, and hence absolutely for every z. Right? Hence uh, gives us a function e power z from c to c. And more thing has been checked. I think we don't have enough space now. Some complex differentiability definition. We'll recall that in the question. Okay. So coming to the question, right? So question number one, right? So we have here function from c minus 0 to c, and we have to check limit of f at z if it exists or not. Right. So let us first recall what is definition for limit, and we'll solve them. So we say L belonging to C is limit of f at z if f if for every epsilon positive, whatever epsilon positive you give to me, fz and L, they become epsilon close whenever z is sorry I should write z not here. So whenever z is very close to, whenever z minus z naught, they are very close, is less than delta. uh, for every epsilon positive, there should exist delta positive such that this happens. No, no. Is this the case? Right. This is a definition. So from the picture, it will be clear that uh, right, given any epsilon positive, we should get. So we should initially we take this to be interior, or I should just write whenever z is very close to z naught. Like, do you understand this definition?
Yeah, yeah.
Okay. So, so in the definition of continuity, what we should take in place of this L, we just replace by f of z naught, and that becomes limit is equal to function value at the same at that point, and that is the one way to check continuity of f at z. Okay. So this is definition. Now another way to write this is, there's no other way, because it was discussed in the classroom. It was discussed. There are two, three equivalent definitions, but I think this will work for us. Okay. So in this case, if you see z is approaching z naught, then fz is approaching L. Okay. So see, in in the complex plane, if you have some z naught, there are many ways to approach z naught from left, right, or whatever direction. So, but we need to check at zero, right? So at zero, we'll check, maybe we'll calculate delta, or simply to discard an option, we'll go these two ways. From x-axis and from y-axis, we need to approach zero, and f of z should approach to some L, right? So fz is equal to first part, a fz is equal to real part of z. So what do you think? Limit should exist or not? As z tends to zero, real part of z is also becoming zero, right? Because you see, z is equal to x plus iy, and if you apply f on this becomes fx. Sorry, this just become x. We are focusing on real x. When x plus iy goes to zero, it means x also goes to zero, y also goes to zero. So from here x goes to zero. That means if you're going to x-axis this way, you're getting 0. So is this fine?
Yeah, here we should like to be very strict and formal. Like if we are asked to provide the function for delta, like
Okay.
in beginning real
Let
analysis, so we can just put delta equal to e, right? Like or we are
equal to epsilon. We can use this inequality whenever needed. Real part of z, this is real number, this is less than, or we take modulus of this is less than mod z,
mod z. Okay.
and epsilon is equal to delta will work, right?
Um, so one thing in these limit definitions, right? Like whenever z minus z naught is less than delta, implies that fz minus limit is less than or equal to delta, or it is less than or equal to epsilon, or it is less than epsilon. Like
Less than
how
epsilon.
is it usually like?
Okay, let we apply the definition,
Hmm.
we'll get this. Uh, we write a formal proof for this, but we understood at least what should be choice of L. Choice of
Yeah,
L
yeah.
is, so now we know that L is equal to 0. So let epsilon positive be given, and the first guess was that delta is equal to epsilon for me, but for general, no one knows. So we start with fz minus L less than epsilon, and we want to show when we want to get a delta, right? So from here, this less than epsilon means fz less than epsilon, because L is equal to 0. Our guess is, but fz is equal to real part of z. This is same as real part of z. Modulus of this is less than epsilon. When it is less than epsilon, this suggests us, now this comes to picture, uh, that whenever this suggests us whenever uh, mod z is less than delta, real part of z is also less than mod z. This implies real part of z is less than mod z less than delta. So what is choice of delta we should take so that it holds? Delta, if we take epsilon, delta equal to epsilon will work, because when, so this suggests us to take delta is equal to epsilon. So Now we just write the definition. Now we verify that whenever mod z minus 0 or z minus 0 is less than delta, this implies fz minus 0, this is fl, right? So in other words, mod z less than delta implies real part of z is less than epsilon, because epsilon is equal to delta and real part of z is less than epsilon. Okay,
Okay.
so this much is all we need. The downside part, all this work, this upper side is just rough work. This
Yeah.
this is
Oh,
rough
but
work,
coming up with that for various, even if the functions become slightly complex, right? Even in real analysis, it is not that easy to come up with that delta epsilon. Like, suppose
right?
something like, and in complex numbers, many weird functions can be defined, right? So, and this will affect the suppose there is some tricky function, and we want to find the inverse, then
Mm.
continuity, then differentiability, and all those things. So this has to be very formal, right? Like, that's why I'm asking again and again, like.
I understand. So this is difficult part, difficult question to come up with a delta. So we go backward. So we initially take less than epsilon, and we go at the end we want a choice of delta. Just like in the previous day when I was going, uh, after taking d delta ball, I pick some point and I want to choice of epsilon if there is d1 ball, right, contained inside the bigger ball.
Yeah.
So I go on from back calculation. I initially took that, let's say it is less than epsilon and whatever. So at the end we calculated that such as epsilon exists, and that
Okay.
epsilon was depending on delta, which was right defined that way. So in the most of the cases, what happens? We should go backward,
Backward.
right,
Okay.
and find some choice of delta. If there does not exist delta, so you can never get delta. So you still don't know about. But the guess
That
is
is the problem, right? If we can't get that clean function, right, we will always be doubting that, okay, is it continuous? Does the limit exist or not?
right.
So then we cannot go to the. I mean, usually the question will be on differentiability or something related to differentiability. So like some other deeper conclusion. But if the first step itself we are not able to provide, then and thank you for working this out. And like from now on, I don't think I'll ask this. So.
Okay, there is one thing. So most of the time, things are clear. You know some basic calculation, and you see the picture. Most of the time, it becomes clear. So what should be delta and something like that, right? So
Okay.
first option is correct here. Let's say second option. What do you think about 1 by z? When z tends to 0, where 1 by z goes? Let's say we are going through real axis. Now it becomes real sequence, right? Let's say from plus side, if you go, let's say sequence 1 by n, so it is going to plus infinity,
Yeah.
right? From minus side, you go, it becomes minus, it goes to towards minus infinity.
Yeah.
So it doesn't exist. If you see some, so there is limit of f, you can check this way also. When xn goes to 0, where fxn goes. If function is having that limit at that point at 0, so the same limit will be given. Like here, fz converges to L, so every sequence also goes to L, right? So that is sequential criteria of calculating limit.
Okay.
So
Uh, Here I've got another doubt, like this, another very basic, maybe trivial doubt, because actually I'm just coming to math after a long time. So
okay,
this limit equal to infinity and limit does not exist. So what I understand from this the limit of a function as this point goes to this point is equal to infinity means all the any path you take to that function, it will reach the same plus infinity, one infinity. And
More.
if any of the from different paths, if it gets different infinity, plus infinity, minus infinity, or maybe plus infinity and some number, then the limit doesn't exist. Is that the correct understanding, or like
No, no, no. This is not correct way. So whenever it is infinity,
hmm,
plus infinity or minus infinity or whatever, we
hmm,
say it is not existing. Until and
okay,
unless we get a special complex number, fixed complex number,
okay.
where it converges, we say it does not exist. Simply. So saying that it is going to infinity is a wrong way to say. So it doesn't.
Because some texts do say that, like some texts or some lectures do say that, if yeah, okay, and in real analysis they are saying like, but if it is going to plus infinity and minus infinity, of course they are saying, like, no, it doesn't exist. Uh,
Yeah. We should say it does not exist because we
okay,
are not getting any complex number where it converges. That is good way to say. Okay, B is wrong.
okay.
Why? Because 1 by n goes to 0, but f of 1 by n, which is equal to n, does not exist. But this limit 1 by n tending to 0 does not exist. So let's see part C. E power z minus 1 divided by z. Okay. So part C, we have e power z minus 1 divided by z. This is our f. Now, from the basic calculus, if you see, when you just put the value of z, if it is, we are done. E power z is also continuous and differentiable, whatnot. Uh, Minus 1 is also the same. It is becoming now rational function. E power 0 minus 1 becomes 0 divided by 0. It is something like 0 by 0, and that is not valid. Now we need to check with some other way, right? So what is e power z defined as? E power z what defined as 1 plus z by 1 factorial plus z square by 2 factorial and so on, right? From here, take minus 1, subtract minus 1 from both sides. So what it becomes, z plus z square by 2 factorial, right? Z cube by 3 factorial and so on. And still, to form fz on left side, we should divide by z. So this becomes e power z minus 1 divided by z is equal to 1 plus z square by, sorry, z is, we are taking z common. Okay, z by 2 factorial plus z square by 3 factorial and so on. And now, just like e power z, this series, it is verified that it is absolutely convergent. This is also absolutely convergent. Okay, I don't want to prove here, but proof is similar. Okay, so if you take z is equal to 0 now, these two functions are equivalent. One side is series, of course, but it is absolutely convergent series. So as a function, these two functions agree on c minus 0. Okay, so at 0, if you want to check limit of left side function, you can check function of right side. So put the value of 0, and it becomes that limit of f as z tends to 0 is equal to 1, because this part is becoming 0. Only 1 remains. Now you have some idea that limit L is equal to 1. use epsilon delta definition, get some delta, and you will of course need to see the that this part is becoming zero as z tends to. Okay, is this making sense?
Yeah, yeah. The
So
only quibble is like, see, for real numbers we can do the epsilon, right? Epsilon delta is fairly clear, but when it comes to complex numbers, when we actually do like, say, a epsilon a plus I epsilon b square divided by, uh, again we like go to that, yeah, we have to use modulus in that definition, right?
yeah,
And
yeah,
okay.
we we use always modulus definition. So we always go to real numbers, and there we have definition of how close, how far points are. Because when you take length of maybe area of your house or whatever, we always get positive real number, not complex number. Okay.
Okay.
Okay. Yeah. So here it goes to one. It here does not exist. Here it is going to zero. Now we have another function e power 1 by z. Of course, you just take the. We need to check at zero. So 1 by n sequence, if you take, what 1 by z becomes? It becomes n. If you go through 1 by n, e power f, e power n goes to infinity. It means it does not exist, right? If you are going one way to zero, and that function value is becoming very large, always becoming larger, 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 we say does not exist, because there's no other. If converges at some point, it should be bounded, but it is unbounded. That makes this function that does not exist. So this is wrong, or we should say does not. Understood?
Yeah, yeah.
Right. So last part is about z into sine 1 by z, and we have to check what is where f goes when z tends to 0. Yeah. So one other thing is to check limit. It's sequential criteria that I'm using in the fourth part. When xn goes to 0, f of xn goes to L. Whatever xn you take, it should go to L if it is converging then. Okay. So if you take z is equal to maybe 1 upon 2 pi I, or not I, you just take 2 pi n or n pi, 2 pi n or n pi, doesn't matter. So if Zn is this, then Zn converges to 0. Zn is going to 0. That is clear. Where f of Zn goes.
Can we use that, like in real analysis we are using that sandwich theorem, right? Like, uh, my that is, absolute value of x and the top v and bottom v, so the sign must come in between them and must, like that we do.
Right? But
Here is it possible, like,
here we are not using that. Here we are just using when Zh goes to 0. When Z goes to 0 or Zn goes to 0, doesn't matter. Fz should go to, or Fzn goes to L. And we want to guess an idea where what should be L, right? So when we take Zn is equal to 2 pi 1 by 2 pi n, so it is going to 0. This is clear. Where f of Zn goes, put the value of 2 pi n. So inside sine, what it becomes 2 pi n, right? 1 upon 2 pi n into sine 2 pi n. Now sine 2 pi n is always 0, right? So this is going to 0. This gives an idea that what should be L. L should be 0, right? Do you understand?
Yes. One more like slightly philosophical question, like sign of the complex number. Okay.
Right,
So how can we define it? We just have to expand it into like e to the power I theta minus e to the minus I theta divided by 2, like that. The
right.
definition will go like that, or like it has got some other meaning.
There in the classroom it was defined like uh, using some power series, right? And there we get the formula for sine z. Whatever you are saying is correct. So that way we can calculate, and it will be a complex number only. Now,
Okay.
one more thing I would mention here, that inside real number, if you take sin z is bounded function, right?
Yeah.
Bounded
Yeah.
between +1 and -1.
Yeah.
But here it is not clear. You need to verify that it is unbounded.
Okay.
Some Sometime we will see this. Oh, next lecture maybe. If we get
Okay.
some extra time, we'll discuss that. It is unbounded on complex numbers. Right.
Okay.
So here in the last part, we get an idea that limit should be 0.
Okay.
Now, I think it does not exist. So I will find another sequence where Zn goes to 0, but f of Zn does not go to 0. So if it exists, it should be uniquely existing. So the last part, we don't have enough space here, but we'll do here, E part. So if you take, so we have function z into sine 1 by z. So the problem is at 1 by z, when z is equal to 0. So that is why my guess is that it does not exist. We'll create some sequence. Let's say zn is equal to 2 by pi, so that when we invert it, it becomes pi by 2. You understand that this is wrong. And after 1 pi by 2, I want to reach at the same point again. So we need 4 pi 2 pi plus. Okay. So we add 2 pi every time. So 2 pi n. This is my sequence. Oh, oh, it does not make right. So it should go to 0. Okay. Adding 2 pi n in the denominator, so that when we invert it, it becomes numerator, right? Yeah. Plus 2 n pi. So we are dividing everywhere. So we should write it 4 and 5. So now you see it becomes 2 by 5. No, no, not 5. You cannot have it. Right. From here it is clear that it goes to 0. Is this clear? Because in the denominator, uh, n is going to infinity. N is becoming larger and larger.
Yeah. Yeah.
Yeah. So now put what is f of zn? F of zn is uh, pi plus
1.
4n pi,
4
this
and
divided by 2 into sine, same thing, 4n pi. What is this inside value? That always becomes 1. 4n pi plus pi by 2, or so sine of this is equal to sin of 2n pi plus pi by 2. What is this? This is always 1, right? You understand that?
yeah, yeah.
So we put that value 1 here. Now where fzn goes? This is rough calculation. So where fzn goes? From here, this implies fzn does not exist because this n here, this says that is going to fzn does not exist. Okay, so we found two sequences, one which goes to 0, but f of the n goes to 0. But here another sequence, one which is going to 0 is clear, but f of the n, this goes to infinity. This means limit does not exist. Okay, so party is also almost clear, I think. So if you don't understand, you can ask me. Now maybe we are friends. Okay, so let's see next question. Z is equal to e power 2 pi I divided by n, and n is bigger than or equal to 2. So first of all, we draw unit circle so that we know, uh, because all these values e power I theta belongs to S1 for every theta inside real. Okay. Now where are these? So Z is given, right? Z is e power 2 pi by n. So what will become Z power n? What is Z power n? This is e power 2 pi I, and we need to get 2 pi angle. So this becomes, what this becomes? This value. This becomes 1 because here it is 1. This is I. This is minus 1. This is minus. So e power 2 pi I becomes 1. So from here it is clear that Z power n minus 1 is equal to 0. Z satisfies this equation. Z complex number satisfies Z to the power n minus 1 polynomial. And from here, if you see Z is equal to nth root of 1, right? So it is the root of unity is clear. Any doubt here?
No, this,
No doubt.
this is yeah.
Yeah. So now draw all the diagram. Sorry, draw all Z powers of Z. Where is Z? Z is somewhere here. So Z square will be somewhere here, because argument principle says if it was theta, what it will, argument of this will become Z square will become 2 theta, right? So every time you are adding theta, so Z square will be somewhere here where it is also theta, right? Every time you are changing with theta. and so on. This way, at the end, it will be somewhere here e power or z to the power n minus z to the power n minus 1, and z to the power n becomes 1. This is clear, right? So z is not equal to 1, of course, z is here. So this is also true. Okay, it's just that you calculate the value of z. Now z to the power k is equal to 1 or unique integer. This is correct.
Yes.
No, no, it is not correct. Think from,
Oh, okay. Unique means okay. Multiple integers are there for which.
yeah, yeah,
Oh, okay.
correct. So you understand that. Just e power 2 pi I. So for C part, I'm writing here. If you add, sorry, plus n, if k works, then k plus minus n
Plus or minus nk we can write because
c
anything.
will also work, right? So this is it wrong. Last part is about this. So you see this is factor of z power n minus 1,
True.
z power
True.
n minus 1, sorry, minus 1 is factored as z minus 1, 1 plus z power, right? Is this factorization of polynomial clear? How we get this? You just multiply, it will be clear, right? Just z power n will be this and minus 1 at the end. Everything else gets cancelled. Now, since z is not equal to 1, z minus 1 is non-zero. Non-zero things inside C, they are invertible, right? So, but z to the power n, this is equal to 1. This implies z to the power n minus 1 is 0. So, on the left side, it is 0. So z to the power n minus 1 divided by z minus 1. Here it is unit. This is unit, means non-zero inside C is equal to 0. This implies 1 plus z to the power n minus 1 is 0. Okay, right. So the last part is correct. If there is problem, you can ask. There is one more other proof I think we can see. So if you have polynomial, n degree polynomial, you have n roots also. Sum of the root क्या होता है? What is sum of root? So if you have polynomial
Coefficient
a
of
naught, a1,
degree.
a plus and so on plus a n minus 1, z n minus 1 plus zn, then sum of roots let
A1, A1.
a n minus.
Okay, sorry.
I'm
Yeah.
writing in different manner. Sorry. So this is sum of root. But in this polynomial, there is no factor, no term of z power n minus 1. So that's why it is 0. And this is sum of root. Because all the root, these are all the roots. This z, z square, z cube, z power 4. This is roots of unity there. Sometimes in the literature it is written omega, omega square, omega cube, this way. Okay, so the sum of roots is 0 here. So you can prove anyway. This is good way, I think, because z is not equal to 1, z minus 1 is unique, but z power n is equal to 1, so z power n minus 1 is 0. So the left side is 0 here in this call star. So the right side is also. Okay, so now we are in the third question, and almost 1 hour is over, and we have 2 3 more questions. Then you can ask other question if you have. Yeah, recall that for a non-zero complex number, argument z is defined theta inside this real number. Okay, and z is not a real number. It is not lying on the real number, so that it has imaginary part, non-zero. Uh, which statements are true? Yeah, I think this question is very much simple. So what is our z bar? How is z bar defined?
Conjugate of the
Z is equal to x plus iy, then z bar is equal to
x minus a.
minus iy. Right. So if z is equal to e r into e power I theta, what is how is z bar defined? R e power minus I theta.
Right, minus theta. E power I minus theta. Yeah.
Just like if it was cos theta plus I sin theta, so z bar becomes cos theta minus I
Minus
sin,
I.
and this
Or you
is
can
e
say
minus
plus
I
I
theta.
minus theta also. That is also sometimes very useful to do actually.
Yeah, so it is e power I theta. So from this much calculation, this becomes easy that argument of z bar is equal to minus of argument. So the second part is correct and first part is wrong. That's clear. Now, how about 1 by z? The next two part is about 1 by z. So if z is equal to r e power I theta, how is 1 by z defined? 1 upon r e power I theta.
One, yeah,
And this becomes 1 upon r e power minus I theta.
I theta.
So argument of 1 by z becomes
Minus argument of z.
right, minus of z. So the fourth option is correct, third option is wrong. Now how about last option? Argument of z1 into z2 is the sum of arguments of z1 and z2. I think it is not correct, right? Because argument is a well-defined function only when we restrict our argument inside minus pi and pi. This includes.
For if you just put into no, it looks true, right? Because if you just say e to the power r1 e to the power I theta 1 into
So z1 is equal to r1 e power I theta 1, z2 is equal
yeah
to r2 e power I theta 2. So z1 into z2 becomes r1 into r2 to e power I theta 1 plus theta 2. So from here it says that argument of z1 into z2 is, but see, this is discussed in the classroom. There it has problem. Argument of z1 plus argument of z2. what is wrong here is that left side belongs to minus pi pi,
Ah, okay, okay. Yeah.
and here this also belongs to same interval. This also belongs to same interval. But it can happen that the sum is becoming bigger than pi. For
Yes.
example, let's say omega cube is equal to 1 and we are taking omega, then argument of z, argument of omega is 2 pi by 2 pi by 3 plus or minus, we can take anyway. Let's say 2 pi by 3. So z1 and z2 both, let's say, equal to omega. So then argument of omega square is equal to minus 2 pi by. But if you sum this twice, it becomes 4 pi by 3, and here it becomes minus 2 pi by 3, right? Both are equal. I am saying as a complex number, they are equal. But as a domain, as a codomain of this function, argument, this should land inside this interval. No?
Okay. Okay.
So
So if you, if you to make this work, we should go mod 2 pi or something like that. Then it should work.
having this, you should modulo this interval. Let's say this interval is I. So modulo I,
Okay.
right? Something like this. So that whenever it is becoming bigger, you can mod out and get something inside. So I'm saying this will be the argument of W, sorry, argument of argument of omega, adding twice becomes 4 pi by 3. But if you
Okay.
go modulo I, it becomes minus 2 pi by 3. Then it
Correct.
is okay.
See, one
So
thing I'm observing in many of these problems is like you have to be very careful about the domain and uh,
code
sometimes domains of definition and all those things. So when
right,
to be careful about that, because in this it is set as a question only, but when we solve bigger problems, like when you want to say multi-stage problems, like when do we say, okay, this guy is like, for example, there are many trivial definitions of open sets in the basic topologies and all those things. So how do you know when that full detailed definition is important, and when we can go ahead very easily, like just add the two things and go ahead? So
actually now in this stage of doing mathematics, so it should be clear that whatever we are taking is we should, it is always important that knowing the domain of definition. For
okay,
example, taking rational function or defining some function and showing that function is inward, means well defined at that point, is continuous at that point, or in this domain it is continuous and differentiable, something like that. So that is only main important thing. So
okay,
someone comes and says that this function is, let's say, invertible, then it is clear that it is defined everywhere and it is one and two function, something like that.
okay,
But it is not clear that one and two type thing, then we should know where to restrict ourselves so that everything works out. Okay.
thanks.
Yeah. Okay. See, let's see. Fourth question. Which of the functions are differentiable at zero? So first, see the definition of differentiability. At zero, we need to check. So we need to check limit. There are many equivalent definitions. So I'm writing this: f of z plus h minus f of z plus h, means here we are taking z is equal to zero. So we put only h, f of f minus f of zero divided by z minus a लिखते हैं, but यहाँ पर a इक्वल टू जीरो है, तो only h टेंस टू, Generally we write z minus a goes to 0, or here equivalent thing can be written like z tends to a, z minus a in the denominator, in the numerator, f of z minus f of a, okay? Or many other notations it has. So what if both are equivalent? This is for general, but here we use this here in this. So this limit exists, then we say it is differentiable. This is the question. Okay, so now we coming to our question. A part is about real part of it. What do you think? It is mostly not a polynomial, not trigonometric logarithm, something like that. So it should be not
Different.
invertible, not differentiable, but it could be. But we'll take limit of this function. So when h is equal to, let's say h is equal to h1 plus I h2, we write, because h is also complex number. Z minus a is complex number. So limit s tends to 0 means h1 h2 both tends to 0, and f of h becomes h1, right? Minus f of 0 becomes real part of 0, which is 0 divided by h. What is this limit value? We'll solve it. Limit h is going to 0. This is same as h1 tends to 0, h2, and in the numerator we have h1, in the denominator we have h1 plus I h2. Now you see here, if we go via x-axis, h2 is equal to 0 always. h2 is always 0, right? If we go via real axis, so in that case is equal to 1 uh, when h2 is 0, or when we are approaching 0 via x-axis, it is z. But if we approach via y-axis, what happens? It is always 0 because there is no real part. Real part is always 0. h1 is always 0, right? When, so let me write, not write it this way. There's two possible limits. There are more possible if we change our path, right? Limit fz z tends to 0 is equal to 1 when z tends to 0 along x-axis or along real numbers, and 0 when z tends to 0 along y. This is clear?
Yeah.
Okay. So doesn't exist. If it was existing, it should have been unique. So it is not different. So it is wrong. Now we are checking for modulus. See, right. So we are using always first definition. So we want to check limit mod of h minus mod of f0 divided by h s tends to 0. So mod of h divided by h, what is this? When we approach via x-axis, mod h becomes h. H also becomes h, and it becomes 1. So this is equal to 1 when h is real number. H belongs to R or approaching via x axis. Mod h divided by h. No, no, no. Going from left and going from right, it becomes +1 or -1 depending on going
Yeah.
approaching 0 from the left or approaching 0 from the right. So here it is wrong, of course. Now it does not exist uniquely, so doesn't exist. So it is also, so the choice is clear now. So I don't need to write that. When mod z is always positive, but yes. So about mod z square, we again want to write this thing, limit s tends to 0 and mod h square minus mod 0 square quotiented by h. Will this limit exist or not? Mod z mod h square divided by this. This can be written as h into h bar squared. This becomes h bar. And now when s going to 0, so h1 plus I h2, h1 also goes to 0, h2 also goes to 0. This implies h1 minus I h2, here again using the same thing, also goes to 0. H bar is also going to 0. So this becomes, okay, when we write here limit s tends to 0, limit s 0, it becomes 0. Right. This is it. So this limit exists. So principle at 0 is clear. If you have doubts, you can ask. These are simple calculation, I think you understand. So in the fourth part is same as first part, and it is most likely incorrect. Imaginary part of that. But how will you prove? You should get two sequences which are going to 0, but after applying f, they are going to different places, right? Either they do not exist or they exist but they're different. One is going to maybe 0, another is going to maybe 1, something like that. So D part is, I think I should know. You can. About we move over to the Z bar. So Fz is Z bar, and we want to check limit of s tends to 0, h bar minus 0 bar quotiented by h, if it is exist or not.
We have already done this in that part C, right?
No, no, part C, this was existing because of extra h bar. It becomes 0. Because it was modulus square, we were getting in the numerator extra h square.
Okay, okay.
Extra h.
Okay.
That's why
Sorry,
it
I get
becomes
it.
0.
Sorry.
But yeah, but here it is not equal. This is let's plus 1 when approaching y-axis, right? Plus 1, right? Because h bar is same as h if and only if h belongs to real number, and they get cancelled from numerator and denominator. It is always plus. But when h is equal to oh means pure imaginary, then it becomes minus, because h bar becomes minus of h2 and h is ih.
No, when it is real, it is always one. When it is imaginary, it is plus or minus one. If I'm, as, am I thinking correctly? Like,
It is always minus 1 when it is imaginary,
okay, yeah, okay,
because h bar is equal to h1 minus ih2.
yeah. So whatever it will be inverted from the down. Okay, that is minus one. When it is belonging to R, it should be only one, right? Like only plus
Right,
one. Yeah,
right.
not plus or minus. Yeah.
So it is just plus 1 when it is real. When it is purely imaginary, it is minus. So this is also incorrect. Now we are going to the last question, and then we'll see if you have extra doubt. If class problems, you can ask. F is an entire function with the following are. So what about z square? Z square is a polynomial. It is entire function. I'm saying. Are you agreeing with me? All polynomials are entire functions. Their derivative exists everywhere. It was done in the classroom. Okay, and f is entire function. Z square is entire function. So composition of these two functions f and z square. This is first one. It is entire. Or you can write as a composition or product of functions of f into f. This is then it becomes f square. Okay, so we can write it in two ways. There were product rules of differentiability. How you differentiate a product? You just, let's say f1 into f2 है, then f1 into f2 prime plus f2 into f1 prime. This is derivative. So that way it is always differentiable. And f is already entire, so no need to worry about it, right? Now we are going to see second row. So first is clear because composition of differentiable function or composition of differentiable function, but not entire function is entire. I should right. But in the composition, it should be clear that when you are checking differentiability at z naught, f differentiable at z naught and g differentiable at f z naught. This is this would give differentiable at f of z naught. Then composition is differentiable at z. These two things would be uh, as a hypothesis, and not at when we see that when we say that g is differentiable at z naught. This is incorrect. Its correct way is saying g is differentiable at f of z naught. Okay, and then f of c, sorry, c, when we calculate prime at z naught, what it becomes? G prime at f z naught into f prime. So this could be the hypothesis. But f is entire function. It means f is differentiable everywhere, and z square is also differentiable everywhere. So no need to check as is at it. It's just by hypothesis. It's entire. Okay. But part B, how about part B? F is entire function. This is incorrect. clearly, can you say what we take fz is equal to that identity? You don't take it. Whatever that is, and this is entire, right? Because it is solid. What z of z is equal to z bar, and z bar is not differentiable at zero. We just see in the previous question, right?
Yeah.
Is not entire. Um, Entire function means differentiable at every differentiable at z or everywhere, right? So how about part C? Part C is composite of two functions. First function is, let's say, z minus a. Let's say this is f1, z is equal to z minus a. Then f2 is equal to f. So when we write this composition f1 composite f2, this becomes C. See, f is also entire, z minus a is polynomial. Both are entire. F is, this is y hypothesis. So this is entire. So this is correct. So how about last part? Again, take f is equal to identity. F fz is equal to z. I'm giving counter example. So this is counter.
Yeah, just use the z bar, z conjugate,
Then
like
z becomes zz becomes
z,
just z bar
z conjugate.
and not enter. Right. So this is incorrect again. We are done. If you have any doubts in the classroom, maybe some definition of compactness or connectedness, you can ask. Otherwise, we'll end this like this session. 2 minutes. So whatever I have discussed today, I think because you have gone through the classroom, everything is clear. No, polar representation, rational function, uniform convergence. So uniform convergence is something people forget about, because what is important here? The most important thing is getting common and not for every day.
Uh,
And about power, you can ask.
just one thing, like if you can expand a little bit, maybe 2 3 minutes on how connectedness, compactness, the differentiability definitions, right, can be applied to complex numbers also, for especially that inverse definition of differentiability, inverse sets definition of differentiability to that is not done in the class, but if you have some insight into that, uh,
I don't understand. Inverse means
in if a function is differentiable, every inverse is compact, or every inverse is like
no, no,
what.
no. If this is not done, but one thing is that pre-image of open set is open. This is by
Yeah,
definition
yeah,
of
yeah, that is the one. Yeah.
okay. So okay, we can discuss little bit about continue.
Mm.
So f from C to C, this is continuous if f inverse of u is open for every u open. Yes. Whenever u is open here, preimage of open set is open. This is one way to say continuous definition. Another way is when xn goes to x, or I should write zn because we are in complex numbers. When zn goes to z naught, continuous, this is continuous at, so here you see the point is not mentioned, single point is not, but here we say f is continuous at z naught. That definition is for every z naught is a continuous. F is continuous at z naught if for every zn sequence zn converging to z naught, f of z naught, f of zn also converges to f of z. So this is sequential definition of continuity. And there is epsilon delta definition of continuity that for every, so same thing. Can we copy it? Oh, pasting here. We could have written right written again. Yeah, f is continuous at z naught if for every epsilon positive, what we have, there exists a delta positive such that f of z and f of z naught, they become epsilon close whenever z and z naught, these two complex numbers are delta. So this is a silent delta definition, this is sequential definition, and this is topological definition. If you want to see, I can show that all three are equivalent in complex.
Yeah, all these and differentiability. Like this week, sir covered differentiability in the notes. So to this definition, like how can we add something so that even differentiability becomes like thing that that condition is that like limit must limit must equal what the limit that is for continuity. So from here, can we do differentiability in a easy way or like that is tough?
Yeah, differentiability, you have to calculate that limit. So these notions are basically point wise. So
Okay.
continuity at z naught, differentiability at z naught, something like that, and you have to find the limit.
Okay.
And there
And
is
the
no,
only way to know differentiability in complex thing, there is no like easy topological definition like how they have for continuous.
there is
Uh,
no something like that, right?
just we have to calculate the limit, and if the right hand limit, left hand limit, everything exists and it is exactly equal, then only like it can happen.
Yeah, that this 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 is not a good definition for differentiability, and it is not. Something like this doesn't hold for difference. This that is exactly that is notion of uh, purely analysis, not topology. But
Okay.
limit is a notion of topology. Calculating limit,
Hmm.
this is a notion of topology, but we cannot have this way that knowing a open set. Yeah.
Okay. Thank you so much for the explanation.
Okay. So we will have next week, maybe Saturday at 4 p.m. next session.
Yeah. Okay.
And
So like
other
every time you will meet on this time and date only, like that I can.
Saturday only. Yeah.
Okay. Thank you so much.
I can write my email address. You can question if you have question. You can ask me any anytime. This is my email address. AMNS dot M. Okay, so I'm ending the class here. See you next week.